In this video, we're going to use the Python package PhiFlow to run a super simple simulation of a smoke plume using only 50 lines of code. Let's get started. Hi and welcome to this new video. As said in the intro, we're going to use the PhiFlow Python package. PhiFlow is a suite of simulation tools for partial differential equations that is built upon deep learning frameworks like TensorFlow, JAX, or PyTorch. It can be used to perform so-called differentiable physics, which is a clever combination of simulation techniques and adjoint methods to interleave simulation and deep learning. But here we will only look at the simulation part. We are going to simulate the incompressible Navier-Stokes equation in conjunction with an advection equation. So we have a fluid that is within a box that moves according to the Navier-Stokes equation, and within this fluid there is a smoke, a species embedded, which follows an advection equation. So we're going to solve the momentum and incompressibility equation for the fluid's velocity. And this will then be used in the advection equation to move our smoke through the domain. The smoke is also hot and thereby exerts a force due to buoyancy into the fluid's momentum equation. So that's the way these two equations interact. So as said, we will be having a closed box, so a square domain where the boundaries are given according to walls. And then we have a circular patch in the bottom left of our domain where we will insert hot smoke. This hot smoke is rising up due to the effect of buoyancy, and then by the incompressibility in our Navier-Stokes equation, we will see this smoke plume creating that you've also seen in the intro, and we're going to animate it interactively. And PhiFlow is a cool tool because it allows us to simulate those kind of phenomena really easily. And we're going to use a solution strategy that is based upon heavy operator splitting. So we're going to perform all the individual steps in the equation one after another. For this, we will start with a 0 fluid velocity and a 0 smoke density on our entire domain. For the fluid velocity, we're going to use a staggered grid in order to avoid pressure oscillations. I will also have a video linked up here where you can learn more about the staggered grid. For the smoke density, it is fine to use a centered grid. Then the first step in our simulation step is going to advect the smoke densities according to a McCormack step. And hereby we will use the fluid velocities from the previous iteration in time in order to advect our smoke densities. Then we're going to add the inflow force or the inflow source to our advection equation in order to simulate the additional inflow of hot smoke into our domain. Then we're going to compute the buoyancy force by resampling the smoke densities onto the staggered grids. So we have to do some grid transformation, aka interpolation here, but we will see PhiFlow is going to do this for us under the hood. Then the next steps are concerned with the fluid. First, we're going to convect it, so self-advection, by using a semi-Lagrangian scheme. This is also directly implemented in PhiFlow. And then we just add the buoyancy force. And finally, we have to ensure that our fluid is incompressible. And we do that by solving an additional elliptic equation and then subtracting a pressure correction. But this is also done under the hood. And then we're just going to repeat the steps over and over, depending on how many time steps we're going to take. And this list of steps might indicate that we are not adding any diffusion here. And that's by design. So for the simplicity, I chose to not add diffusion here, but rest assured, the convection and advection procedures, so the numerical techniques we're using here, are adding considerable amount of numerical diffusion. So we will have some form of numerical diffusion, although we don't use it like explicitly here. Of course, this would also be possible to do within PhiFlow. Okay, then let's close the terminal here and start with the actual implementation. For this, we will first import the packages. So we, of course, need the PhiFlow package. So we will do from phi import flow, and then this flow abstraction will collect all the major functionality of PhiFlow. Then we're also going to need matplotlib for visualization. So import matplotlib.pyplot as PLT. And then I will also import TQDM. So from TQDM, import TQDM as a super simple progress meter. Let's also define the number of time steps to be 150. You can, of course, augment that if you like. Then let's define a main function, leave it empty for a second, and get our main switch done, such that our file is only executed with the Python interpreter. Then we need to define our two major fields. So this is the velocity field and the smoke, so the species field. So let's start with velocity field. Velocity is going to be our staggered grid. So we will do flow.staggered grid. And then this staggered grid takes a couple of arguments. So first we have to define its values. So the values of the velocity vectors on this grid. And as said, we're going to have the fluid at rest in the start, so 0 and 0. Then we have to define a so-called extrapolation that allows us to prescribe our boundary conditions, and you can think of it as the values in a layer of ghost cells around the domain. And here I want to set this one to 0, which prescribes a wall boundary condition. Then let's set the extent of our domain in terms of its discretization points, and I want to have 64 by 64 discretization points in our two-dimensional mesh. And these are going to be used on a physical domain, which we're going to define by the help of the bounds. And for this, we'll be using a flow.box with an extent of 100 units by 100 units. So this means we have a physical size of, for instance, 100 centimeters by 100 centimeters, which are discretized using 64 by 64 points and a staggered grid. Next up, we have the smoke, which is our density species embedded into the fluid. And as said, we wanted to use a centered grid here. And also this smoke is going to be 0 at the beginning. So this is its initial condition to say. And for the extrapolation, we're going to use a way in order to prescribe a Neumann boundary condition. So we'll be doing flow.extrapolation.boundary. And here, this boundary, we can also see the documentation, is going to extend the grid with its edge values and thereby prescribes a Neumann boundary condition. This centered grid is going to be more high resolution or of a higher resolution by 200 by 200. Here we go. And its bounds will of course be the same as the velocity. So we will also be using a flow.box with x being 100 and y being 100. Because of course, these two grids shall overlap in a sense. Then these are the two fields, but I also want to predefine the inflow pattern to our smoke. Because remember, this was this circular patch in the bottom left. So we're going to define an inflow object, which is going to be a centered grid again, and it will look quite similar to the smoke. Except, of course, here it's not going to be 0, but it's going to be 1 inside the circular patch and 0 outside. And we can set that by using a so-called soft geometry mask. And this soft geometry mask allows us to define geometrical primitives in our domain. And in this particular case, we want to use a sphere, or in 2 dimensions, a circle, and this one shall be located at 40 units in x and 9.5 units in y direction. It shall have a radius of 5, and this should define our circle. And as said, this will set the values inside the circle to 1 and outside to 0. I just want to scale that down a bit by multiplying with 0.2. Here the extrapolation shall be 0. But it does not greatly matter because it's just our inflow pattern. In order to get that defined, we will also set the bounds, but here we will make usage of the smoke field that we already defined. So we will have smoke.bounds defining the bounds of our inflow pattern. And for the resolution, so in essence, what we defined with x and y here, we're also going to use smoke.resolution. And then let's use these fields in an update routine. So I want to define a step function which should take a velocity previous and a smoke previous. So smoke values and velocity fields from the previous iteration and a time step. And here I will just set this one to 1.0 for a super simple simulation. So then as said, the first step is to advect our density field, the smoke. So we will do smoke next is going to be flow.advect.McCormack applied to the smoke previous and the velocity previous with the dt as we defined it here in our default value to the step function. And as said, this will use a McCormack routine in order to advect our smokes using the velocities from the previous iteration. And then I just handily add the inflow that we defined in order to prescribe our source to the smoke field. This new smoke field can then be used to define our buoyancy force. So buoyancy force. And for this we will be using the smoke next multiplied with 0 in x direction and 0.1 in y direction. So because we want to have the buoyancy forcing upwards, because that's kind of how you would see the hotter smoke creating forces that lets our fluid move upwards. And then as said, this kind of requires an interpolation and a remapping from the centered grid of the smoke field to the staggered grid of our fluid field. And that is easily done by the add operator. And by this we can resample grids within other grids. And here this allows us to resample our centered grid in the staggered grid of our velocity field. So you can think of it, multiply the smoke field with this, and this kind of extends it to a vector field with 0 in x components and 0.1 times the corresponding scalar value of the smoke field in y direction, and then resample this field on the locations of the velocities in our velocity staggered grid. Well, then we can use the buoyancy to get a tentative velocity step by first advecting our fluid according to a semi-Lagrangian scheme. And if you've seen previous videos of mine, the semi-Lagrangian scheme is what is commonly done within the stable fluids algorithm. I have a video linked up here if you want to see how to implement a semi-Lagrangian scheme yourself. And for this basically takes the velocity previous and the velocity previous. And this also highlights that this is a self-advection scheme, so we will use the fluid to advect the fluid, which kind of gives us this nonlinear convection that we see in a Navier-Stokes equation. And then we have a dt according to our time step, and then we will just add the buoyancy force multiplied with the time step size. And I used the tentative because the velocity is according to the next time step, but it is not incompressible yet. So it does not adhere to this incompressibility constraint that you find in the Navier-Stokes equation. So let's try to make it adhere to it by also using a routine from PhiFlow. So this routine is going to be flow.fluid.makeIncompressible. Kind of verbose, right? And this makeIncompressible takes our tentative velocity, and then it does some magic under the hood, building a correction equation, solving it for us, and it all does that kind of abstracted away. And this returns two quantities. So first, it returns the velocity next, and it returns a pseudo pressure, which I just want to capture here in order to have the returning pattern of the makeIncompressible function right, but we will neglect this pressure here. And then we are basically done with our step routine. We can return the velocity next and the smoke next, and this is the update. And as you see here as well, we only use advection routines and then buoyancy force computation and incompressibility routines, but we are not using any diffusion routines. You can of course add them, but here as said, these advection routines also introduce some form of numerical diffusion. Okay, well then let's use this step function repeatedly in order to visualize a simulation. So let's do for underscore in TQDM a range of n time steps. This will be our main simulation loop, and we're just updating our velocity and smoke fields by saying velocity comma smoke equals step applied to velocity comma smoke. And then we have to visualize our field. And for this, we first have to make a transition from the PhiFlow world back into the NumPy world. So we will say smoke values extracted, and we can extract them from the centered grid by saying smoke.values.numpy. And then we have to provide a way to PhiFlow in order to remap the centered grid into a NumPy array. And in order to adhere to the convention within Matplotlib or also NumPy, we're going to use y, x, which first has the y-axis and then the x-axis. Then we can use Matplotlib with the imshow command in order to plot the two-dimensional array. So we will use smoke values extracted. We're going to set the origin to lower to have our smoke plume rising upwards and not going downwards. And then we will just use some boilerplate in order to get the animation interactive with a plt.draw, a plt.pause with 0.01, and a plt.clf to clear the figure. And then just let's have a dark mode, because why not? So plt.style.use dark underscore background. And that's already it. That's the entire simulation, given we haven't made any mistakes. So let's run it. Let me clear the screen and the Python smoke plume. And here we see we have a missing argument. And of course, I think, yes, I called it value and it should be values. Let me check with the documentation. Yes, it is values. So here we go. Let's try it again. And here we go. So we have this start. Yep. And it is simulating. We're doing about 1.4 iterations per second. And you see the smoke plume is rising. Fantastic, isn't it? That was really simple, wasn't it? Of course, you will find this source code file in the video description to play around, maybe add some diffusion if you like. But this might now seem a little bit slow, also in comparison to what you've seen in the intro. But now I want to show you a really nice feature of PhiFlow. So for this, let me first stop the simulation. And in the beginning, I said that PhiFlow builds upon the deep learning frameworks like TensorFlow, PyTorch, or JAX, and we can not only use them in order to kind of build the deep learning aspects within simulations, but also to accelerate our simulation by using their more sophisticated implementations of certain aspects of NumPy. Well, I mean, let's just do it, and then we will see it get faster. And we can just do that by a quick change in the import by saying from phi.jax import flow. So of course, if you have JAX installed, if you prefer PyTorch, you might want to use phi.torch or phi.tf. So you're kind of flexible to use this deep learning framework you personally prefer, or that you also already have installed on your machine, because I think installing JAX on some Windows machines is rather tedious, but I will go for JAX here. Feel free to change that to TF or Torch, depending on your machine. This allows us to run all of it in JAX. So let's save it, run it again, and then we will see, oh man, it's even slower now. What happened? What did we do? And we haven't used the big feature of PhiFlow yet. So because we haven't even gotten a first iteration. Now there is it. And well, this takes forever. So let me just cancel this. And the big feature is that we can use the just-in-time compilations of these deep learning frameworks in order to accelerate our code. So let's go to the step function and add a decorator with the @ sign and say addflow.math.jitcompile, and that's already all we need. So let's go back again and restart the simulation. And we now have a longer startup because we have this compilation happening, but once it's compiled, hell, it's going really fast. So let's get here and you see, well, now we're doing 6, 7, almost 8, well, around 7 iterations per second, and you see the smoke plume rising in real time. Isn't that beautiful? So you see kind of this buoyancy force driving our flow upwards. You see the flow is respecting the wall boundary conditions, and we have this swirly motion due to the incompressibility. So that's the end of the video. I hope you enjoyed this quick intro to PhiFlow. You will find the link to the source code down in the video description. Also check out the GitHub repo of PhiFlow and feel free to create a pull request on GitHub if you have some additions to the simulation code. I would be really happy to see what you come up with. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. There are going to be more PhiFlow videos on this channel in the future, so subscribe to the channel if you don't want to miss that, and like the video if you enjoy this kind of content. Here you will now see similar videos, and I hope to see you in one of the next videos.